Okay, just a quick little 3x3 system of equations. We use Gauss-Jordan to solve that. So before we start building our matrix, we want to do two things. One, I want to check and see if I could conveniently reduce any of these equations. For instance, if there was a 6 in front of this z, 2, 2, 6, and 4, I could divide this equation both sides by 2. But there's no convenient way to do that. The second thing I want to do is typically I want to put my smallest lead coefficient on the x's. I have 1, 3, and 2. I want to put that first. And if we have a 1, by all means, we want to put that row first. I can list these in the matrix any order I want, equation 1, 2, and 3. But I like that there's a 1 here. So let's set this up. I've got 1x, no y's, negative 3z's equals negative 2. 3x's, 1y, negative 2z's equals 5. And 2x's, 2y's, 1z equals 4. So the process, we want to start in that top left corner with this 1. This is my first hired hitman whose responsibility is to whack this 3 and this 2. And we analyze this 1 and 3. The least common multiple of 1 and 3 is 3. both these numbers go into 3. So these are going to match at 3. Since this is already 3, I'm going to turn this 1, our hitman, into negative 3 by multiplying this row by negative 3. And we're going to go pay a visit down here. In our second matrix, the hitman row does not change. 1, 0, negative 3, negative 2. But now we're going to physically touch 1 times negative 3, negative 3, added to 3, 0. Well, that's why we did it. Here's kind of a bonus 0, makes life a little bit easier. 0 times negative 3, 0, and 1, 1. Here's 9, negative 3 times negative 3, 9, plus negative 2, 9 and negative 2, 9 minus 2, 7. 6, positive 6 and 5, 11. Okay? And the next job is for 1 to whack the 2. They match at 2. I've got a positive 2 here, so I'm going to create a negative 2 in this position, multiply by negative 2, and go pay a visit to the third row. Touch them. I get negative 2 and 2, 0. Well, I better. That's why we did it. I get 0 and 2, 2. I get 6, positive 6 and 1, 7. And I get positive 4 and 4, 8. And then after each step, there's a couple things, to each new matrix that we create, there's a couple things we probably want to do. In the event you can reduce a row conveniently, I would do so. Well, we can't. But if this was 2, negative 10, and 8, we could divide this row by 2. But there's not a convenient way to do that. We'd have to create fractions. And then the second thing is understand these two rows could switch. But my next hitman position is right down the diagonal right here. And I love having a 1 there. So I'm not going to flip-flop those. But maybe if this was a 9 and I had a 1 here, maybe I'd want to switch the rows. It just makes the computations a little bit easier. You don't have to do that, but you probably want to. So this guy is in charge of whacking this 0 and this 2. That's a good news situation there because we don't have to, we're already a 0 up here. That won't typically be the case. So this is just one little step. The first row is going to stay the same. 1, 0, negative 3, negative 2. The hitman row always stays the same, 0, 1, 7, 11, and now I need a 1 to whack a 2. The least common multiple between those course, is 2. So since I have a positive 2, I'd like to turn my hitman into negative 2, multiply by negative 2, and send it down. So touching, we get 0 and 0. We never lose a 0 we work to get. Negative 2 and 2, 0, our purpose. Negative 14 and 7, and it's not a bad idea to write those down when you got some multiplication going on, but negative 14 and 7. So you might not need to do this, but it's not a bad idea just to use a little scratch room over there, scratch paper. So negative 14 and 7, negative 7, negative 22 plus the 8 is negative 14. And now we want to see if we can reduce a row, and we certainly can. I'm going to divide this row by negative 7. So we've got 1, 0, negative 3, negative 2, 0, 1, 7, 11, 0, 0, divided by negative 7, 1, divided by negative 7, 2. So what we just learned there is that 1z equals 2. We've got our z value. Okay. Next job, reduce if we can, but there is no reducing to do. So write down the diagonal. We started in that position, this position, this position. Now, you need to understand this could be a 5. It's not the most, wouldn't be the most convenient, but I'd have to work, if this was 5, 2, I'd have to work with this 5. And the 5 and the negative 3 would match at negative, or at 15. Therefore, we'd have to multiply both rows. This row by 5, this row by 3 to get 15s and a negative 15. But the 1's very convenient. 1 and 3 match up at 3. I've got a negative 3. I want a positive 3. Multiply by 3. And head up there. So 0 and 1, 0 and 0, 3 and negative 3, that's why we're doing it, 6 and negative 2, 6 and negative 2, 4. So we just learned 1x is equal to 4. 1 and 7 match at 7. I've got a positive 7, need a negative 7, so I multiply 1 by negative 7 to get it. And I've got, touch them, 0 and 0, 0 and 1, negative 7 and 7, 0, that's why we did it, and negative 14 and negative 2, negative 16. 0, 1, 0, 0, 1, 2. Now, normally at this stage, or often at this stage, I should say, this might not be a 1, this might not be a 1, this might not be a 1. Like this could be a 3 at this time. So then we just have to realize, in the event that was the case, then we just have to realize this means 3 times y equals negative 16, if this was a 3. And then we'd have y as negative 16 on 3. But the 1s, this is a pretty nice little problem for us. This is kind of a beginner level problem on these. It's pretty convenient. So 1x is 4, 1y is negative 16, and 1z is 2. I hope that helps.